they have in them? If we read through our note activity.
They have the other variable.
They have the other variable, yeah. We call that our parameter. A lot of times it's going to be a t. The other one that we can see quite often is a theta. So a plane curve is going to be the graph of a parametric equation. That has both a path and direction. Your direction is going to be represented using arrows. So the path is going to look like any of our other curves or lines that we've seen in the past. But now we're going to have to add in direction, which is what our parameter, basically that third variable, allows us to do. So some applications of parametric equations are if you're looking at projectile motion, if you're looking at landing something, either on the Earth or on the moon, okay? You need to have very detailed information about both your horizontal motion and your vertical motion. And like how the time is affecting it. Like I need to know, is this thing moving to the left and I need to overcorrect that? Or is this thing moving to the right and I need to overcorrect for that? So the direction matters. And just with a normal xy equation, we can't see like how our x or our y are changing over time. We just have points. And so having an x equation in terms of t and a y equation in terms of t allows us to see what direction we are moving on our path. So your parameter is the third variable. That x and y are written in terms of. And most of the time you're looking at either t or theta. Just depends on what type of motion you're looking at. And then your parametric equation is going to be the x and y equation. And so a parametric equation actually has two parts. It has an x part and a y part. So if you're asked for a parametric equation, you actually have to list two equations to make one, because they have to have a horizontal part and a vertical. What questions do we have so far? So far, yeah. And like some of us have seen, it actually makes some pretty fun graphs if you look at them. Because the nice part is that now, since x and y are separate, we can actually get things and represent things that are not functions. Okay? Now, the equations for x and for y will be functions, but what we end up with doesn't necessarily have to be a function. So, here we have a parametric equation. It gives us x equals t squared minus 4 and y equals t divided by 2. It specifically tells us that we're looking at negative 2 to 3 for our t values. And it wants us to sketch a curve. So what do we want to do to sketch a curve? What do we tend to make? And you practice on Friday. When we first started graphing out lines or graphing out anything, what did we make to graph points? A table, yeah. The only difference here is that instead of having a T chart or a T table, we actually have an H table. Because now our X and our Y are dependent upon that T value. Yes. Now, what number do you think we might want to start at? Negative 2, it gives us that we are going from negative 2 to 3. And we just get our x and y value by plugging this t value into our equation. So like if I do negative 2 squared minus 4, what do we get? 0. And if we do negative 2 divided by 2, and so now we just have the point 0, negative 1. And we will plot that in just a second. Now what do we get if we plug in negative 1 for our x? And for our y? And if we plug in 0 for our x equation? And for our y? Yes, are we all seeing where we're getting these numbers from? So then I should get negative 3, comma, 1/2, 0, comma, 1, and 5, comma, 3/2. So then I'm just going to graph those points. So where is the point 0, negative 1? It's on our
Y.
yes. Okay. And then the point negative 3, negative 1/2 is in which quadrant? Yes. Just slightly, right? Because we're only down negative 1/2. And then negative 4, 0 is on the and then negative 3, 1/2 is basically the opposite of this. 0, 1. And 5, 1.5. What does that look like? If we were to trace that. What kind? Yeah, like that. Okay. Now that's our path, right? But I said that our equations or our graphs have both a path and what? Direction. So which point did we plug in first?
0, negative 1.
Okay, and then which point did we plug in next?
Negative 3.
Okay, and then what happened when we got to negative 4, 0? We switched directions, so we turned and we started going to the right. And so basically we just draw little arrows on our graph that indicate the direction that we're going. Yes? What questions do we have there? Okay. Now, sometimes it's going to be helpful to eliminate the parameter, which basically means to get rid of that t, to put it back to rectangular equations, which is just the xy stuff, okay? Or it's also called our Cartesian points, yes? Someone not sorry, had not heard. Do we know what a Cartesian plane is? No? Okay. That's just your xy plane. So Cartesian points are just xy points. Because Descartes was the one that came up with the graph system, and so he got it named after it. So it's called the Cartesian plane. There you go. And so you'll see it both. Rectangular is usually what it's like now is more called. Like Cartesian plane is like the older term, but sometimes you'll still see both in your textbook. So to eliminate a parameter, like I said, we're finding the rectangular x, y equation. So we're first going to solve in one equation. Then we're going to plug the result into the other equation. And then simplify. Now that's if we have something that looks kind of like what our last one was, where we have t's and they're both just like functions. Okay. However, we are going to look at another example. If there are trig functions, we're going to have to use some formulas or equations. So what equations or formulas did we learn that deal with trig functions? That maybe convert them from one thing to another.
Identity.
We're going to use our trig identities. So this unit is going to refer back to a lot of different things that we've looked at in the past. So we're going to have to like delve deep into our filing cabinet of our mind to remember some of those things. Which is good. We're approaching the end of the year, so it's good to remind us of all the things that we've talked about this year. Yes? Alright. So on our next one, let's eliminate the parameter. So instead of like making a chart and graphing it that way, we're going to convert it to just an xy equation and graph that. However, we do need to eliminate our parameter. Now we have 1 over the square root of t plus 1 and y equals t divided by t plus 1. We have to solve for t in one of those. Doesn't matter which one. Which one might we want to solve for? Are you sure?
No.
How many t's do we have on the second one? 2. So like you would multiply by t on one side, and then you would end up having to factor out t's, and it just gets a little not super. No, it's a t on top. Ah, yes, that's t divided by t plus 1. So I would say it's gonna be a little bit easier to solve here. So if I take my left equation, what do we want to do first? Again, we're trying to solve for t.
Multiply square root of t plus 1.
Okay. And then Alan, what do you think? I'm solving for t. What do I need to do next? Well, I already have that, right? That's what I started with. So I'm trying to get the t by itself. So instead of dividing by that, what do we want to divide by? Okay. Then what?
Square the other side.
Square both sides. So I get
Square root of 1 over x.
no. You're squaring, not square
Oh, yeah,
rooting.
you're right.
So 1 over x squared.
I just said square root.
And then what's our last step?
Subtract 1.
Subtract 1. Alright. So now that we have t solved for, what are we supposed to do with that? Plug it into the other one. Okay. So y equals plugging it in for both T's. So what do we want to do first?
Just the bottom is simplified, so it's just 1 over x squared.
Okay. And then what? Dividing by 1 over x squared is the same thing as what? Multiplying by x squared. So then, if we distribute that, what do we get? So what's
We
x
do 1.
squared times 1 over x squared? 1. And x squared times the negative 1 is?
Negative x squared.
So what does that look like?
Difference of squared.
What's that graph look like? What kind? It's upside down, and it's been where? It's up 1 because the 1 is outside of the squared. So it looks like that. Yes? But what's the second part of the instruction say? What's the second part of the instruction say? Just read it.
By eliminating the parameter and adjusting the domain of the resulting rectangular equation.
Okay, so we need to adjust the domain. So it's going to be kind of similar to what we had to do over there, like cutting off a part of our graph. Yes? Now, looking at our original equations, do these have any restrictions? For our t value. Say, so on our first one, t can't be -1, except for y. What about the first one? What are we not allowed to have underneath radicals? Yeah. So what's going to make that negative? Will 0 make it negative? Will -1 make it negative?
No.
Will -2 make it negative?
Yeah. Nope.
Yeah. So what makes it negative?
Anything less than negative.
Okay, so that means that we need t to be,
Right.
can it equal -1?
Yeah.
Can it?
No.
Where is it? In the
Under.
bottom, so it cannot equal it. Yes? So, we just said that if I plug in -1, we get undefined stuff here, right? What do we get if we plug in 0 to our t? So if I plug in 0, I get 1 divided by the square root of 1, which is just, and 1 divided by 1 is also 1. Yes? Okay, and then what do I get if I plug in 0 into the second one? 0. Then what do I get if I plug in 1 Well, what are we going to get on bottom of my x? Square root of 2. That's not a super fun number to try and figure out. What's a different number that might be nicer to plug in there? 3. What are we going to get if we plug in 3?
1 half.
Okay. And then for our y? Okay. Alright. So our first point was at 1, 0, right? Which is here. And then which way did we go? Is 1 half to the right or to the left of 1? To the left. So we're actually going that way, yes? And if I plugged in negative fractions, we would actually get these values, but they are going to be all coming this way. Yes? So we know we're moving to the left, but now let's think about, are there any values for t that I can plug in and get a negative x value? Can the top be negative? Is 1, right? Can the square root be negative? No. So since I can't get a negative in here, my x's can't be negative. So that means that we have to basically cut off the left side of our graph. So it ends up just being that right side. So you would only get half of your parabola for your parametric equation. Yes? Are we all okay with that? Questions? Comments? Concerns? Alright. What does our next one have in it? Trig functions. Okay, what did I say? In order to eliminate parameters on trig functions, what are we going to have to use? Trig identities. Yay! Takes us back. So, if I have a cosine and a sine, what trig identity do we have that relates sine and cosine together? We do have tangent, but then that would add in another trig function, and so that doesn't get rid of the trig function. The Pythagorean theorem, yeah. So we want to use, so remember that we have the formula sine squared of theta plus cosine squared of theta equals 1. Because notice, if I tried to solve for theta here, I would end up with a cosine inverse. We don't really want to deal with plugging in a cosine inverse into a sine, right? That wouldn't be much fun. So instead, I have a sine and a cosine in that equation. So how would I solve for cosine in my first one? Or get the cosine by itself? Yeah. How do I get the sine by itself in my second one? Okay. Well, now I need a squared instead. So what do I get if I square both sides? This becomes cosine squared. And then what do I get if I square the left side? X squared over what? 9. So then what do I get if I square both sides of my second one?
Y squared over 16.
Yeah. Well now, do we agree that cosine squared plus sine squared equals 1? Yes, based upon our Pythagorean theorem. And if I know that x squared over 9 equals cosine squared, and y squared over 16 equals sine squared, I also know that if I add these two things together, just replacing them into that equation, I also get 1. Yes? So basically, since I know that cosine squared is x squared over 9, I can replace my cosine squared with x squared over 9. since I know that my sine squared is y squared over 16, I can replace my y squared over 16 for my sine. So I just get those two things added together. Yes? But now let's think back to something else. What is that the graph of? It's not a circle. It's not a hyperbola. Hyperbola has subtraction. It is an ellipse. Yes? Which side is going to be longer?
Y.
Correct. So remember, I'm going to go up and down 4. Left and right 3. And then just connect everything together. Like something like that. That will be what our graph looks like. So that's our path. What are we missing? Direction. So, we are going to have to plug our theta stuff back in. So I have thetas, I have x's, and I have y's. So what's the thing with sines and cosines that Mrs. Bennett said we needed to memorize because it was going to come up over and over and over again? The unit circle. So we're going to use our unit circle to plug in some key theta values to get our x's and y's. So the first one that it gives us is 0. So what is cosine of 0? Or also if we think about our cosine graph, where does it start on our y-axis? At 1. So then 1 times 3 gives us 3. What is sine of 0? It starts at the origin, so 0. Then we could plug in other values like pi over 3, pi over 6, pi over 4, but all of those are going to give us funky decimal answers. So we're going to go ahead and skip ahead to like pi over 2, and then pi. What do I get if I plug in pi over 2 into my cosine? What is cosine of pi over 2? 0. What is sine of pi over 2? So we get 4, right? And then what is cosine of pi? Negative 1, so we get negative 3. And then sine of pi is still 0. So notice that the first point that we get is this one right here on my x-axis. And then we're going up towards our y-intercept. And then we're going down towards the other x-intercept. And it is going to continue in that direction. And we are moving counterclockwise. Which makes sense because I have sine and cosine. And so both of their angles move counterclockwise.